Problem about thin flexible rope. One end of a thin flexible rope with a linear density ρ is pulled at a constant horizontal speed at a height h above a rough surface. The other end of the rope is free. The length of the part of the rope that is in contact with the surface is L1. Find the length of the rope L2 not touching the surface. The coefficient of friction between the rope and the surface is μ. Solution. First of all, we have to check forces acting on the free end of this rope, which we need to find the length. So we have two ends, end 1, lower end, and end 2, high end. Lower end connected to other part of this rope, length L1, which is pulled by this part of rope, and we can find what is the tension in this first end. This tension exactly equal to force of friction acting on this part of the rope L1. So we have this equation, T1x equal μ ρ L1 G. But from other end, this second end has the tension T2, and we can split it by vertical part T2y and the horizontal part, which is T2x. And this T2x exactly equalized by T1x, because this rope is in horizontal equilibrium. So that's the equation. Vertical part of this tension T2y, it's exactly equal to weight of this free part of rope, because the first end it has a tension exactly horizontal, no vertical part. It means that all weights of this part of rope, it's exactly equal to vertical part of this tension, and we have this equation, T2y equal ρ L2G. And the final thing, which is very helpful in such kind of problems, I can show you by this picture. Suppose that we have a rope which is attached by two ends to two walls, one end and other end, and the height difference between these two ends is h. Let's write this extension for this rope, horizontal extension, and let's put it on this inclined surface, such way that now the surface has no friction, and of course this closed rope will be in equilibrium. It means that we can count what is the tension difference between high point and the lower point of this rope, because now this difference will be exactly equal to part of gravity force acting on this straight line, which is this one. That's mg multiplied by sine theta, where theta is the angle between this inclined surface and the horizontal, and the m, it's a mass of this part of rope. From other hand, mass m equal rho multiplied by L. L is length of this part of rope, and L multiplied by sine theta. That's exactly the height difference between these 2 points. So this is our formula, and this force exactly equal to difference between tensions in high point and low point. So we can write this equation: F equal tension T1 minus T2 minus T1. But tension T2 we can find from this equation, because T2 exactly equal to T2x squared plus T2y squared. And these two tensions, horizontal and the vertical, we already found. That's this one. We can substantiate these parts and get this expression for T2. And the last part is to write this difference, T2 minus T1, that's equal to rho hg, which we found from this picture. And now we can write this equation that T2 minus T1 equal rho gh. We can cancel rho g everywhere, move this part to the right, and square both parts. So we have this equation. Here this mu L1 square cancelled, and finally we have that L2 equal this expression. So this is the solution for our